Hi everyone, let's continue. So how about we have a 3 by 3 matrix. How do we find the eigenvalue and the eigenvectors? So the next example also shows that 0 could be an eigenvalue, even though the 0 vector cannot be an eigenvector. Okay, so let's look at this example 6. This is our A, so the steps are very similar as before. So let's look at A minus lambda I. Well, that is, we subtract lambda from the diagonal entry. So 3 minus lambda, 6 minus lambda, minus 5 minus lambda. And all the rest, all the other entries stay the same. Okay, so we want to compute the determinant. So what is the determinant? So the determinant A minus lambda I is... Okay, so what is the determinant? Let's use the cofactor expansion. Let's use this one. Okay, then it's this guy. So it's 3... By the way, this is a plus minus plus. So plus 3 minus lambda times the determinant of the submatrix 6 minus lambda minus 15 2 minus 5 minus lambda. So far so good, and because all the other entries are 0, so we don't have those. Okay, so let's continue. So that is 3 minus lambda. Well, here we cross multiply. So 6 minus lambda times negative 5 minus lambda minus negative 15 times 2. Okay, what is that? So remember, our goal is to factor it completely. So the 3 minus lambda, just keep the factor there. Okay, and then what's inside? 6 times minus 5 is negative 30. 6 times minus lambda is minus 6 lambda. Minus lambda times minus 5 is plus 5 lambda. Minus lambda times minus lambda is lambda squared. And then negative become positive 30. Alright, so that's 3 minus lambda. Let's reorder it. So that's lambda squared. How many lambda? Minus lambda. Right, so minus lambda. 30. Oh, they cancel. Can you see the common factor lambda? So we have, So we have 3 minus lambda. We factor out lambda, then we have lambda minus 1. See, we have 3 distinct eigenvalues. They are 3, 0, and 1. Okay, so 3 distinct real eigenvalues. So let's calculate the eigenvector for each of them. So you can see 0 can be an eigenvalue. It just cannot be an eigenvector. So lambda equals to 3. Okay, so V is, now we have 3 by 3 matrix, so the V should be 3 by 1 column vector. So X, Y, Z. And then we want to have A minus lambda I times V equal to 0. What is the arithmetic coefficient matrix? A minus lambda. What's A minus lambda? So 3 minus 3, 0. Oh, the first row zeros. And then negative 4. 6 minus 3, so 3. 16 minus 15, and minus 3 minus 5, minus 5 minus 3 is minus 8. Okay, so let's see. Let me see, do I make a mistake? No, right. Okay, yeah, that's right. Okay, let's continue. So the last row, last column is zeros. Okay, so let's see. Let's swap row 1 and row 2. And then we have minus 4. Let's move row 1 at the end. Okay, so we're swapping all of them. So row 1, now my row 2 is gonna be my row 1, my row 3 is gonna be So swap all the rows, move the row 1 in the last one. So because for the action form, we want the row consist all the zeros to be the last row. Okay, so now can you see 16 is a multiple of -4? So we use 4 R1 add to R2. -4, 3, 2, 0. -4 times 4 is 16, -16 plus 16 is 0. 4 times 3, 12. 12 minus 15, -3. 4 times 2 is 8. 8 minus 8, 0. Oh, okay. So we get action form. This is X, this is Y, this is Z, this is the right-hand side. What does the last row, the second row tell us? -3y equal to 0. So Y is 0. So far, so good. Let's plug in the first row. So minus 4x plus 3y plus 2z is 0. Then y is 0. So 4x equals to 2z. X equals to 2 over 4, which is z over 2. So v is then x is z over 2, y is 0, z is z. So we can factor out the z. We get 1/2, 0, 1, z. And we can pick the z to be, if we want all integer and the entries, we can pick z is 2. Then the v is 1, 0, 2. So this is the eigenvector associated to the eigenvalue of 3. So far, so good, everybody. So you can see this step is very similar to what we have done before. It's just the matrix is bigger, so it's more complicated. Okay, next, lambda equals to 0. Well, lambda equals 0 means A minus lambda is our original matrix A. Okay, so keep this in mind. Let's put it down. Okay, so still V is X, Y, Z. Our matrix A is 3, 0, 0, minus 4, 6, 2, and 16 minus 15 minus 5, 0, 0, 0. So far, so good, everybody. Okay. Well, you can see here, I can divide by 3 in the first row. Then have 1, 1, 0, 0, 0. And then I can use this. I want to save some space steps. So because it's 1, I can use it to keep all the entries below it. And I will get zeros, but all the rest will stay the same. Because all this guy are 0, it won't affect the other entries. So here we're doing 1, so 4 R1 add to row 2, -16 R1 add to row 3. This is like step per step. This is the first step and this is the second step. Okay, I combine 2 steps into 1 step. All right, 6 and -15. Let's see, how do we get 1? All right, how do we get 1? That's hard, right? So, can you see the row 3? So row 3, we have a constant multiple of -5. So divided by -5, row 3, we get 1, 0, 0, 0, 0, 6, 2, 0, 0, 3. Oh, can you see the second row? All of them has factor 2. So let's do that as well. So 3, 1. Oh, 3, 1. Oh, do you see they're the same? So we can then use minus row 2 add to row 3. And you can see eventually, I put too many zeros. Okay, 1, 0, 0, 0. Okay, so you can see eventually we will get the last row only consists of zeros. That's always the case when we're looking for eigenvalues and eigenvectors. So x, y, z, right hand side, second row, 3y plus z is 0. So y is -z over 3. First row, x is 0. So v is x is 0, y is minus z over 3, and z is z. So v is, so we can pick z is 3, then we can get integer entries. V is the 0, minus 1, and 3. So far so good. So this is the eigenvector. Okay, let's continue. I don't have enough space. Okay, let me just create more space. Do I have more space? Yeah, should be. Okay, so we still have v lambda equals to 1 to solve. Okay, so lambda equals to 1. Okay, so in that case, v is still x, y, z, but then a minus lambda, well, a is, okay, so keep that in mind. This is a minus lambda. How can I copy the whole thing here? Okay, so I can copy here, paste. Okay, all right, so keep that in mind. All right, so a minus lambda I, 3 minus 1 is 2. 0, 0. Negative 4 stay here. 6 minus 1, 5. And then 2, 0. 16 minus 15, minus 5 minus 1, negative 6. So far so good, everybody? Okay, now let's see. Oh, I can divide it by 2 for the first, for R1, row 1. Then I have 1, 0, 0. Then because it's 1, I can use it to kill the entry below it and without worry about changing the other entries. So far so good, everybody? Okay, now let's see what happened. Oh, by the way, I forgot to put, I'm doing for R1 add to R2, negative 16, R1 add to R3. By the way, can you see now the third row is 3 times the second row? So we can do 3R2 plus R3 to kill the third row. Okay, so this is x, y, and z, and this is the right-hand side. Second row tells us that 5y plus 2z equals 0. So what is y? Well, y is then minus 2z over 5. So I hope your 2 and your z look different. Sometimes it's very easy to write them look similar. Okay, and then the first row tells us x is 0. So v is 0, negative 2z over 5z. We factor out the z, negative 2 over 5 and 1z. So we can pick z. What do you want to pick z to be so that all the entries are integer? Yeah, 5. Then v is 0, negative 2, and 5. So this is the eigenvector. Okay, so you can see in this problem we have 3 distinct eigenvalues, and each of the eigenvalues we can find one eigenvector. So the total linearly independent eigenvector we can find are 3. Okay, and because the matrix 3 by 3 dimension 3, we expect 3 eigenvectors. Yeah. Okay, good. Next, eigenspace. Let lambda be a fixed eigenvalue of the n by n matrix A. Then the set of all eigenvectors associated to the lambda is the set of all non-zero solution vectors of the system A minus lambda I times V equal to 0. The solution space of the system is called the eigenspace of A, associated to lambda. This is a subspace of Rn. So last time we also talked about if V is the eigenvector, then a constant multiple of V is another eigenvector. So actually they generate eigenspace. Is a vector space. Okay? Example 7. Find the basis of the eigenspace of the matrix and also tell the dimension of the eigenspace. Okay, so the basis of the eigenspace is the eigenvectors. Okay, so it's just a different way to ask us to solve the same thing. Okay, so let's do it. Start with A. Okay, so why don't you pause the video here and try to work on the problem? Okay, are you done? Let's check our work. So this problem is actually harder than the previous problem. You might say, oh, but the last problem is already so long. Oh, you will open your mind today when we finish this problem and the next problem. Okay. All right, ready? Go! So 0 equals to A minus lambda I. What's A minus lambda I? Subtract lambda from the diagonal. 3 minus lambda. I always write those 3 entry first, because after you subtract lambda from the diagonals, all the rest stay the same. Okay. Ooh. Determinant. How do we calculate it? Cofactor expansion. Choose one of the row or column. So here all of them have the same difficulty. So let's use the first row. So this is plus, minus, plus. Okay, that means 4 minus lambda, negative lambda, negative 2, 1, 3 minus lambda. See, all the things we learned are actually connected. Determinant. And then minus, negative 2, the determinant of submatrix 2, 2, 1, 3 minus lambda. And then we have plus 1 times 2 minus lambda, 2 minus 2. Okay. Continue. 4 minus lambda of negative lambda times 3 minus lambda minus negative 2 times 1. Minus minus become plus 2, and then 2 times 3 minus lambda minus 2 times 1, which is 2. And then 1 times everything is that thing. So 2 times minus lambda, 2 times minus 2 times minus lambda. So let's calculate what this is. So this is negative 3 lambda plus lambda squared, and then plus 2. This is 2 times 3, 6. 2 lambda minus 2. This is 4 and plus 2 lambda. Okay, if you can remember the last example, we have these two entries are 0, so much easier. But here it's not, so we actually need to multiply out. Okay, so let's see. 4, so hide the minus lambda, so 4 distribute. 4 times negative 3 lambda is negative 12 lambda. 4 lambda squared. And then plus 8. Okay. Minus lambda times 3 lambda plus 3 lambda squared. And then minus lambda, minus lambda cube. Minus 2 lambda. Okay. So that's the first term. Second term, 2 times 6, 12. 2 times negative 2 lambda is minus 4 lambda. 2 times negative 2 minus 4. Minus 4 minus plus 2 lambda. Okay. Let's combine the like terms. How many lambda cube? Negative lambda cube. How many how many lambda square? 4, 3. So that is 7 lambda square. Okay, and then how many lambda? We have negative 12 and minus 2 and oh, so this guy cancel with that guy, right? We have minus 12 lambda and minus 4 lambda. We have negative 16 lambda. And what's the constant term? We have 8 and 12, that's 20 minus 4, so 16. Let me see. So we have 8, and then here we have oh, and then we have minus 4, so we have 12. Okay, so and we want to set it equal to 0. That's the characteristic equation. So how do we solve? This is a degree 3 polynomial. So let's make the leading coefficient to be positive. So let's multiply by negative 1. Then we have lambda cubed minus 7 lambda squared plus 16 lambda minus 12 equals 0. Okay, so this is degree 3 polynomial. Do you remember how we can solve this degree 3 polynomial equation? By the rational root theorem. So we talk about that in session 5.2 and 5.3 when we talk about higher order linear ODE with constant coefficients. Okay, so what are the rational root theorem? Let's look at factors of the constant term. The constant term is negative 12. Well, that's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Okay, and we also look at the factors of the leading entry is 1. Okay, so that's plus or minus 1. Then the possible roots are use this guy divided by that guy. Well, divided by 1 minus 1 is the same thing, so we get the same thing. Let's copy it down. Okay, yeah, so you can see in general a degree 3 polynomial, well, it's gonna be a long work, okay? So we need to use the rational root theorem to help us to find one root. Let's try. So let's try lambda equals to 1. Okay, so let's call this p lambda. So p of 1 is 1 cubed is 1. 7, 16, 12. Is that 0? No, right? So 6 plus 16, 22 minus 12 is 10. So this is greater than 0, not 0. So 1 is not a root. Okay, we continue. Let's plug in minus 1. We plug in minus 1. Minus 1 cubed is minus 1. Minus 1 square is 1, so minus 7, minus 16, and minus 12. Oh, it's all negative. It can't be 0. So you realize we cannot pick the negative numbers. The root won't be negative number because then all the terms are negative. We won't get 0. So lambda, let's try 2. Sometimes it really depends on the problem. Maybe we're lucky enough we find the roots faster, and if we're not lucky we find the roots, we need to go down the list longer to find the roots. So 2 cubed is 8. 7 times 4 plus 16 times 2 minus 12. Okay, that is 8 minus 28 plus 32 minus 12. That's negative 20 plus 20. Oh, yay! We get 0. So lambda equals to 2 is a root. Well, that means lambda e minus 2 is a factor. And then, good. So let's use long division. Long division, we have lambda cubed minus 7 lambda squared plus 16 lambda minus 12. Okay, over lambda minus 2. Well, lambda square, lambda cube minus 2 lambda square. Okay, minus 7 lambda square minus become plus 2, so we get minus 5 lambda square plus 16 lambda minus 12. So, and then we have minus 5 lambda become minus 5 lambda square, and then minus become plus 10 lambda. And then we have 6 lambda minus 12, which is 6. 6 lambda minus 12. Oh, yes. So we always get the remainder is 0 because this lambda minus 2 is a factor. So we have lambda minus 2 and then lambda squared minus 5 lambda plus 6. Can we factor it? Yeah, we can factor it as negative 3 and negative 2, right? So you can see here, lambda minus 2, we have 2 copies of that. So you can see here, lambda equals to 2 is a repeated root with multiplicity 2, and lambda equals to 3 is a root with multiplicity 1. We have 2 eigenvalues. Okay? Then for each of the eigenvalues, let's find the eigenvector. Yeah, it's a long problem. So you will open your mind today. Okay. All right. So first case, lambda equals to 2. V will be x, y, z. And we're solving a minus lambda I. V equals 0. Okay, so how does that work? Oh, what is my A again? So our A is, that is our A. Let me copy it, so I don't need to flip the page again. Okay. I cannot put it here. Let me see. That's my A. Okay, so A minus lambda. So 4 minus 2 is 2. That stay the same. 0 minus 2, negative 2. The rest stay the same. 3 minus 2, that's 1. Oh. And augmented coefficient matrix, the last column, zeros. Can you see all of them are the same? So we can use minus R1 add to row 2, minus R1 add to row 3. So we have 2 minus 2, 1, zeros. Ooh, they're all 0. Nice. Okay, what does that mean? Well, this is x, this is y, this is z, this is the right-hand side. So the leading entry is this 2. So you can see y and z, they are free variables. Okay, so we have 2x minus 2y plus z equals 0. So 2x is then 2y minus z, x is y minus z over 2. Okay, so we get v is y minus z over 2, y, z. What are the coefficient of y? That is 1, 1, 0. What are the coefficient of z? That is minus 1/2, 0, and 1. See, we have 2 eigenvectors. Okay, so the eigenvectors are Okay, so these two are the eigenvectors. Okay, so what is the eigenspace? The question is asking the eigenspace. So the eigenspace is generated by these two eigenvectors, such that y and z are real numbers. Okay, so this is how we express the eigenspace. And what is the dimension? Okay, by the way, what's the basis? Okay, the basis is the set containing the linearly independent vector that generates the vector space. Okay, and you can see because we have two vectors in the basis, the dimension is then 2. Okay, so that's the case when lambda equals 2. How about when lambda equals to 3? Okay, so when lambda equals to 3, we need more space. Okay, let's see what is it now. When the lambda equals to 3, well, let's move this here now. Yeah. Okay. So V is x, y, z. A minus lambda I times V is 0. A minus lambda, 4 minus 3 is 1. 0 minus 3, negative 3. Oops, that's 1. And then 2 minus 2, 3 minus 3, 0. And then the last columns are zeros. Okay, so let's see. Oh, okay. So we can use the 1 to kill the entries below it. So negative 2 R1 add to R2. Negative 2 R1 add to R3. 1 minus 2, 1, 0. 2 minus 2, 0. Negative 3 minus 2 times negative 2. Negative 3 plus 4, 1. 1 minus 2, negative 1. Okay, and then next we have 2 minus 2, 0. Negative 2 minus negative 2 times 2. So negative 2 plus 4, which is 2. 0 minus 2 minus 2. Oh, can you see the second row is, we can use the second row to kill the third row. So we can do minus row 2, add to row 3. 0, 1, negative 1, 0. 0, 0, 0, 0. Yes, we always get the last row just zeros. So this is x, this is y, this is z. This is the right-hand side. And then the second row tells us that y minus z is 0. So y equals z. First row, x minus 2y plus z is 0. So x equals to 2y minus z, but y is z, so 2z minus z is z. Oh, x, y, there, z are the same. So v is x is z, so z, z, z. When we factor out the z, we have 1, 1, 1. Okay, so we can pick z to be 1, and then the eigenvector is 1, 1, 1. Okay, this is the eigenvector. Okay, so what is the eigenspace in this case? Oh, it's just one-dimensional subspace of R3. Okay, so Z in R. And what is the basis? Oh, just consists one vector, the 1, 1, 1. And what's the dimension? Yes, 1. So far, so good. So this is how we solve example 2. It's actually quite long because in general, a 3 by 3 matrix is not easy, right? You first when you compute the determinants, you have to do the cofactor expansion. And in order to solve the lambda, you have to multiply everything out so that you get a nice simplified formula for the degree 3 polynomial, and then you use the rational root theorem if we have a rational root, okay, then it works. Then you keep, so we might have a long list, so you just go through the list until you find one root. So after you find one root, we can use long division, and then to get a quadratic factor, we can either factor it or use quadratic formula to find the remaining two roots. And here we can see we have a eigenvalue 2 is repeated, so we might have 1 or 2 eigenvectors associated to it. Okay, and then so lambda equals to 2, this is the way how we solve it, and we realize we have two free variables. We in fact get 2 eigenvectors associated to it. Okay, and the basis has the 2 vectors, dimension is 2. For the eigenvalue 3, we solve it and realize we have 1 eigenvector. So the eigenspace is this guy, and the basis just consists of 1 vector. We have the dimension is 1. Okay, so that is example 7. And there is a challenge example 8. So example 7, even though it's long, I didn't say it's challenging, but example 8 is challenging. So let's see how we can solve example 8 in the next video, part C. Yeah, sometimes you can solve one example for the whole class. Okay, see you soon.